This is the first of 6 videos on characterization methods used for organic chemistry. Proton NMR spectroscopy will gain most of the attention. 4 videos set to just discussion of proton NMR spectroscopy. There'll be a single video, lecture video on C13 spectroscopy and infrared spectroscopy, all of these involving light. Then the last video will be on mass spectrometry. So we have 4, 1, and 1. As far as videos go, covering characterization methods used in organic chemistry. This first video is just an overview of NMR spectroscopy, whether it be proton or C13. And what I want to do is just discuss the very important 3 players in the drama we call NMR spectroscopy. You need to have a little field. This is from the sample. A big field. This is where the money is in the instrument. You have a huge electromagnet or a permanent magnet in the NMR. And the climax of the play will be due to a applied radio frequency from the instrument to the sample. So we're going to talk about that. And I'd also just like to finish this discussion, intro on NMR spectroscopy, by looking at the basic principle of how we can capture the chemical shift of certain protons in compounds, how we can separate those chemical shifts on some x-axis and look at the spectra and sort of the details of that spectra, what we can see from that spectra of a compound. So just a little bit more than just the introduction to the 3 players in the drama. We'll talk a little bit about the data. In the next 3 videos after this, we're going to focus in on that data, where we look at 3 parts of the data. We look at 3 parts of the data that have to be pulled out, or looking at structure, 3 bits of data that have to be put in. We need to know the number of non-equivalent protons, because this will give us the number of maximum signals in the spectra. Integration will tell us something about the number of these non-equivalent protons. So the number of non-equivalent protons will be reflected by the area under the peak, the integration of a signal, the area of a signal. Then the splitting of the signal is going to tell us something about number of neighboring protons. It's not going to be about you, but about your neighbor, the neighboring protons. We're going to find out something about that something about the number of neighboring protons by the splitting of a signal for that particular proton. So this splitting will talk about the neighboring protons. That's going to be in the 2nd, 3rd, and 4th videos. Let's go ahead and look at just NMR spectroscopy, the play itself. So we just jumping down from where we'll be and what we'll look at in detail. Let's just propose a molecule, diethyl ether. What is it about this molecule that we can analyze by NMR spectroscopy? Well, we don't analyze the whole of it. We don't analyze bonds. We analyze just the proton's atom's spin. So what we're going to look at is protons that, as an atom, have a nucleus, and that nucleus we consider by quantum mechanics to have a spin momentum or a spin tensor or a magnetic moment that we can manipulate, that we can sort of throw things at and make it move so that we can analyze the structure. So let's take and look at that proton in a little bit more detail. So let's take the simplest structure, methane. We could say methane has 4 protons, 4 atoms, proton atoms, bonded to this thing in blue, a carbon. Well, if we have a nuclei with an odd number of protons, neutrons, or both, we have a very small magnetic moment or field for that nucleus that has an odd number of protons, neutrons, or both. Well, a carbon certainly doesn't. It has a number of protons that's equal to 6, and the most common isotope has a number of neutrons also equal to 6. So an even number. But the most favored isotope for hydrogen is just a hydrogen with 1 proton as a nucleus, not deuterium, which has a proton and a neutron. So we can see a lot of these protons in NMR spectroscopy because we can influence their magnetic moment. So they have a magnetic moment. We can see a lot of those by setting up the instrument in a certain way. So we have a lot of potential. So each of those 4 hydrogens has a magnetic moment, what we call a little field. Very little. I mean, it's not very strong at all. So we'll just show it as having 4 of these little tensors. A little field. Itty bitty. But that's what's going to be the necessary component for the instrument to work. It has to work on something. Well, it's going to work on these little fields. So they're not pointed in any particular direction. So if we were to take methane and we were to look at all 4 hydrogens, I don't know, I've scattered them about here, but we can just sort of, in a sense, imagine all those tensors, and they're not lined up in any particular direction. This could be lined up that way, this could be lined up this way, his could be lined up over this way. There's not a setting of their direction as far as their magnetic moment. That's where the instrument comes into play. So they sing any way they want it. That's the, any way you want it. That's the way you get it, or whatever that song goes like. But if we take a big magnet, a big field, and we apply it, we can change the orientation of all those magnetic moments that had no particular orientation. We can change them so that they are either aligned with that big field. This is the big field here. This big field that we're creating, let's say the north and the south. And we can have the alignment with that be slightly favored over the opposed state. So we notice the number 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. It's usually very, very small favoring of the line over the opposed. It's not what you would think, that 80% of them align and 20% of them oppose the field. No, it's a very small difference between how many are aligned with the big field and how many are opposed here in blue. So the strength of the magnet can be increased so that we have greater alignment, or percentage aligned, but it's really a very small number. The stronger the applied field, the greater those number that are aligned over those that are opposed can be. The magnetic field of the nuclei does not perfectly align, so this is a little bit misleading. We really have some precession of the magnetic moment around the axis of the big field, some precession. That's really important. These are not perfectly either aligned or perfectly opposed. We're going to key in on this precession about the big field of these little fields. That's important. So we can say they're not perfectly here, we're showing the aligned state. They're not perfectly aligned with that field. They are pointed in the direction, but off angle a little bit, and they're precessing at a very rapid pace around this axis generated by the big field. And the larger the field, the faster this precession frequency. So it's not perfectly aligned. The magnetic moment of the nuclei precesses, or has a frequency around the axis of the big field. So that frequency is going to be different for all different types of protons within a compound. We'll see that in the next slide. We can now bring in the third player of that play. We said there's the little field. That was our first player. You have to have something that can be responsive to the big field. And we, of course, have a little field that responds to the big field, the big magnet. And we've set up the play, because we only have 2 states that the little field can be in. It can be slightly aligned, or aligned, I'll say, and precessing, or opposed and precessing. So we have those 2 states. Now what we could do is apply through a radio frequency coil of wire. We can have a magnetic frequency on the X and the Y, or on the X-axis or the Y-axis, however you want to look at it, this being the Z maybe, everything going in this direction. But we had some precession, and we can grab this nuclei's little field because it has some XY component. Its precession is in a different dimension. Its set value is not changing in the Z-axis. It's going to have a certain length always as it precesses about. But there's going to be some components to its magnetic field that we can manipulate or that we can grab. So as it precesses around this axis, we can influence it by having a magnetic field applied through the radio frequency that is in the X-axis here. We'll call this the X-axis. And of course, coming out towards us would be the Y-axis. So we can have some alternating magnetic field that when it matches the frequency of this precession can cause resonate. It can resonate with that nuclei little field, and we get a flipping of its energy. So once we hit the precession frequency, as soon as we match that, we can get a flipping of that little field. So we apply an alternating current. That's our radio frequency that matches this precessing. Now, of course, this is in just one dimension. This is in the precession is in two dimensions, but we can still match that frequency of precession going as this arrow is going up. We have some magnetic field going up, and as it's coming now down from the top and coming back around to the south, we have a magnetic field applied to the south. As we set the frequency for our applied current, or the radio frequency, as we set that to match the precession frequency, we get some absorption of signal, or absorption of energy. Once we absorb that energy, we can have a relaxation and get our signal. Now, all of this would not work if all we had were little fields that had no electron density around them, because every proton then would have a precession frequency that's equal to every other proton in a compound. So it wouldn't matter, if we were looking at diethyl ether again, if there are no electrons around the protons off of this carbon and this carbon, there's no difference. But of course that's not true. We know the environment for these two hydrogens is not exactly the same electron environment for these three hydrogens, because there's electron shielding around the nuclei, the little field. We can have differences in their precession frequency around that big field. So because this is supposed to be my electron density, this sort of BAM signal, my electron density around each proton is slightly differing. I can have a different precession frequency, and therefore a different radio frequency will excite it. So the field that we actually feel, or this nuclei actually feels, is changed by the electron density. This is what the NMR applies, but we subtract, this is because of electron shielding, we subtract some amount particular to the proton in the structure where it is. We subtract some amount which changes what it actually feels, and therefore changes its precession frequency and makes it unique to that proton. So we now have precession frequencies that can be unique to certain protons depending upon where they are in the structure and how much shielding, electron shielding, we have around them. So electron density is really the key. The change in that around these nuclei can be detected. Let's take a very extreme example, trichloromethane, where we have a lot of inductive withdrawal of electron density to the chlorines, and we have then some inductive effects pulling from this carbon the electrons in this bond from the hydrogen, so it's de-shielded. De-shielded. I'm going to go ahead and put that up here. De-shielding would cause the precession to be faster because we have less electron density around the proton's little field, and therefore it has more effective interaction with the applied field of the instrument. So we call that a de-shielded proton as we move to the left. Now you want to put these together, D and D. and this sounds kind of odd to say downfield. When we have a d-shielded proton, we move to the left and on the spectra, this axis, and that's the d-shielded side, the left side, that's also the downfield side. I'm not going to go into why they call it the downfield side, but you need to know that D and D go together. D-shielded, left side, that's also the downfield side. The right side over here, so we have tetramethyl silane here, so this would not be d-shielded. These three protons, these three protons, these three, and these three are all equivalent. So there's actually 12 protons that are going to give us the same slow rotation. Why slow rotation, or slower than this one? And there's not much of a difference. I shouldn't say really, really slow and really, really fast. These are very small differences as far as on the Hertz scale. They show up in pretty much the same megahertz scale, but there's slight differences in their exact Hertz values, their frequency. That's a slower rotation because silane is not as going to be withdrawing. As withdrawing, it's going to be a fairly covalent bond, and we don't have a lot of pulling away of the electron density from this hydrogen. So this is a very shielded type of proton. In fact, we used tetramethylsilane then as a standard, an internal standard that we set to 0, sort of everything measured against it, for NMR. So it's a very shielded type of proton. There's actually some donation from this to the carbon, so the silane to the carbon, so we can have that donated back. And we also call this the upfield side. Okay. So these two sides of the NMR spectra, downfield and de-shielded is on the left, shielded and upfield side is on the right. Now, we know that radio frequency increases from right to left. We're going to change the way we describe this x-axis. We're going to take away this concern about precession frequency, the exact precession frequency we have measured at any particular point on this x-axis. We're going to take that away. How do we do that? How do we make it measured in just ppm? Well, what we do is we treat every magnet as, well, I guess, let's go ahead and talk about it now. What we do is we take and factor out the strength of the magnet. So what we do is we just look at a difference value, or just a difference over the whole. So this is a difference here in Hertz values here over the, I guess, the strength of the magnet. So the strength of the magnet in the denominator and this difference value, we put those, I guess, together, difference over the strength of the magnet, so that we can factor out the strength of the magnet. Because if this increases, this will increase in the same proportion. So for simplistic illustration, we could say if this was 2 difference to 10, if this went to 20, the difference would go up to 4. So 2 over 10 is equal to 4 over 20. So we factor out the strength of the magnet, and therefore don't have to worry about the exact frequency of rotation. For every magnet, it'll be different because the field strength will be different, the precession frequencies will be different. Well, we can factor that out by using a, I guess, part over the whole, a difference over the whole. We get a ratio, 2 to 10, 4 to 20, 4 to 20. Well, we don't have those small numbers. We have very large numbers. 60,436 hertz minus the strength of the magnet, so that's sort of the difference where it starts, or just the signal for tetramethylsilane. We have some difference against that standard over the strength of the magnet. That would give us what we call a parts per million signal, a relative signal, not an absolute signal. So we can take out the strength of the magnet by using ppm as our, I guess, chemical shift signal. ppm measurement of the signal, or the samples, by ppm and not by frequency. So we've taken the observed chemical shift the number of hertz away from tetramethylsilane over the strength of the magnet. Strength of the magnet over that difference in hertz values. So let's say that tetramethylsilane and trichloromethane spin flips occur at these frequencies. We have the 60 million hertz. We set that as sort of our zero. And everything above that we of course measure. So we have a very small difference, 436 hertz is our difference, and we divide that by the strength of the magnet, and we get this 7.27 parts per million. This would be, again, the downfield side where we see this 7.27 parts per million, and this would be the upfield side, and of course we would set that at 0 parts per million. That is our internal standard. So we would say 60 million hertz minus 60 million hertz divided by 60 million hertz. Well, of course, that's 0 parts per million. So that's how we take away the issue of concern for strength of the magnet. If we would have had a 360 megahertz NMR, then the signal would go up, but to the same proportion. So that difference would still give us 7.27 parts per million as our signal. It's kind of illustrated here. We're almost done. Just looking at bigger magnet, better resolution issues. If we can take that small difference, we said, and increase it, the actual number of hertz that you're dealing with in terms of your range, if you increase your actual number of hertz values, separate hertz values, that's important for resolution purposes. It may not change the chemical shift, but it'll give you better resolution in your data. So here's why. A ppm range in a spectrum has a larger or smaller range of hertz values based on the magnet's strength. So if we have a smaller magnet, 60 megahertz, we may have that difference we talked about in hertz values between 0 ppm for tetramethylsilane and something further downfield, maybe only 60 hertz. But if we increase the strength of the magnet to 200 megahertz magnet, then we have to increase by same proportion to keep that same chemical shift value, the actual difference in hertz values. So that just gives us more hertz values to deal with within that spectra. We have actually more hertz values in the spectra. This one has less hertz values within the spectra. So it's easier to see the same number of people signals spread out on a 200-yard field relative to, compared to, I guess, a 60-yard field, those same number of signals or same number of people. Of course, so we get better resolution, basically, with a stronger magnet. So bigger magnet, better resolution. So let's just kind of wrap up what we've talked about in this video. We said that we have 3 players. We said we have some big field, but we have some little field that big field can work on. And what we work on really in the application of the radio frequency is that component of the little field that's not perfectly aligned with the big field, that precession. And we matched that frequency of precession by applying a radio frequency of the same frequency as that precession frequency. So that was key, those 3 players: big field, little field, and radio frequency. Something we didn't touch on that is new is we can actually, even though there's some amount of electron density around each proton in a sample that's differing, my little cloud of electron density, we can apply a short pulse of radio frequency that excites all the little fields regardless of the difference in shielding they have. So all of them get excited. That's a more current method of NMR. It's Fourier transform NMR, where everybody gets excited all at once. And we get then a signal, it's called the FID, Fourier induced decay signal, where when these relax back, the magnetic moment as it relaxes back gives us a signal we can work with that tells us what the frequency of precession was for each proton. And of course we said we're not measuring in frequency, we're measuring in parts per million to take out the strength of the magnet's concern. The bigger magnet we have, the sharper the peaks, the better resolution. Don't forget that. The bigger the magnet, the sharper your peaks. The more ppms, or more, hertz values you have in any particular part of the spectra, you have more Hertz values, so you can blow it up and you have better resolution because there are actually more Hertz values within the spectra as compared to a smaller magnet. And last, don't forget, this is the downfield side of your spectra, and this is the upfield side of your spectra. Upfield is the shielded side, downfield is the de-shielded side. Well, that's it. Bye-bye.